In this video, we're going to be looking at the internal mechanisms of an electrochemical cell in more detail using the redox reaction involving silver and copper from the previous video. In the previous video, we saw that our anode reaction involves solid copper undergoing an oxidation reaction in which each copper atom loses 2 electrons, resulting in the formation of Cu2 plus ions that are then dissolved in an electrolyte within the anode, and the charge for which, the positive charge of the Cu2 plus ions, is then stabilized by some sort of dissolved negative ions in solution. Nitrate, of course, works best because nitrate will never form a precipitate as long as we have a large enough solution volume. The 2 electrons that are then lost by copper in the oxidation reaction travel down the connecting wire, creating an electrical current that can be used to power other devices attached to this electrochemical cell. When those electrons reach the cathode, however, those electrons are picked up by silver ions that are dissolved within the cathode's electrolyte solution and then precipitate as solid silver metal on the solid part of the cathode here. What we're interested in is what the change in concentration of each of the ions within the electrolytes of the anode and the cathode is going to do to the battery. Now, if we consider the anode reaction here, over time, the more of the oxidation reaction we have, the more copper 2 plus ions we're going to generate, causing an increase in copper 2 concentration over time. Now, this has a number of ramifications as far as the function of our battery goes. The more Cu2 plus ions we produce, the more positive charge we create. Now, there are a couple of problems with this because as our positive charge increases, there is only a finite amount of negatively charged ions dissolved within this solution, and eventually this amount of negative charge from dissolved ions like nitrate isn't going to be enough to balance the positive charge from the copper ions that we're making. Now, why is this extra positive charge a danger? Well, all positive charge is going to attract negative charge, and if this positive charge is strong enough, it is possible that the electrons lost in the oxidation reaction can be attracted back to the positive ions, reforming our precipitate here and regenerating the copper ions here. Now, this isn't a problem until you consider what the purpose of a battery is. If the electrons just come back to their original source, they don't migrate towards the cathode, and we don't get any current generated, which means that our battery is not doing what its purpose is to serve. So the problem is, the more positive charge we generate, the less likely our battery is actually going to function as a battery, which means that we need some way to diffuse, and there's a hint for later, to diffuse this positive charge to a certain area so that we can keep the flow of electrons flowing in the direction that it is suitable to. Now, if we look at our cathode, we actually have the opposite problem. As silver ions pick up the electrons lost in the anode, overall their concentration is going to decrease over time, which has the opposite effect of the anode. Now, remember that our electrolyte also requires negative ions in order to balance the charge, which means as the positive charge of the cathode's electrolyte decreases, that because there are fewer silver ions to provide positive charge, that means that our solution is going to become more negative, and the more negative charge we have, the less likely electrons are to migrate to the cathode because the negative charges are going to be repelling each other. So in conclusion, because the positive charge is decreasing at the cathode, this prevents the electrons from wanting to migrate towards the cathode. So the problem in both cases of our electrodes is that we do not want the anode to accumulate a large amount of positive charge, nor do we want the cathode to accumulate a large amount of negative charge. Now, we can take advantage of two factors, one being the salt bridge, and the second being a large amount of positive or negatively charged ions will naturally repel away from each other and naturally make these ions want to move far away from each other. And that's what the purpose of the salt bridge is. So the point is, these copper ions building up in the anode do not want to stay together. They will naturally want to move to a location that has a large amount of negative charge. So therefore, the high concentration of copper ions will naturally move through the salt bridge, which is its intended purpose, towards the cathode, because at the cathode we have an accumulation of negative charge. Now, simultaneously, the high concentration of anions, because remember that it doesn't have to always be nitrate, as long as there's any anion that will have a soluble electrolyte here, any of the high concentration of anions that's accumulating at the cathode is going to migrate in the opposite direction towards the anode. And in fact, this is where the words anode and cathode come from, because as anions migrate from the cathode to the anode, we get that accumulation of negative charge on the other side, and likewise, as the cations that accumulate at the anode migrate through the salt bridge toward the cathode, we get the accumulation of positive charge here, hence why each electrode is given the name that it is. For the people that recognize the term diffusion, either because you've seen it in biology before or because you remember it from the equilibrium unit, diffusion is simply the process of any particles moving from a high concentration to an area of low concentration, which is exactly what we see with the high concentration of copper ions migrating from a high concentration at the anode to a low concentration at the cathode, and vice versa with the high concentration of anions migrating from the cathode to a low concentration at the anode. This is what the purpose of the salt bridge is. So in addition to stabilizing the charge imbalance, doing so naturally creates the conditions that will allow electrons to keep flowing from the anode to the cathode in order for our electrochemical cell to continuously generate power.